All right, welcome back. We are now on lecture 2, which is going to be a continuation of our review of probability. Today, what I wanted to focus on is my 3 favorite special distributions, and those are the uniform distribution, the gamma distribution, and the normal distribution. So let's go ahead and take a look at those. All right, so first up is the uniform distribution. So I'm sure we all remember how this works. I'm going to describe it by its probability density function. So let's say, so x this time is going to be a uniformly distributed variable on an interval AB. What does this mean? It means that it has the density function has the same value at every point between A and B and 0 elsewhere. So f of x is going to have some constant value c for x in this interval AB. It's going to be 0 otherwise. And you quickly see that because you know that the integral of f of x dx, which is really the integral of c from a to b dx, has to be equal to 1, that tells us that this value of c is actually 1 over b minus a. So we actually have 1 over b minus a, x in AB, and 0 else. This was supposed to be a hard bracket, not that it really matters that much. Okay, and that's the uniform variable. All right, and now the gamma random variable. So the idea of the gamma random variable is a slight variation on the exponential random variable. So just to remind you, the exponential random variable is the one with the probability density function. F of x is lambda e to the minus lambda x. So that's one particular random variable of interest, but it has a generalization, which is the gamma variable. So the gamma variable has an exponential part, e to the minus, I don't know, let's call it bx. But then it also has a polynomial part in front of it, x to the a. Kind of a monomial part. I guess a doesn't have to be an integer. And then is some normalization factor. So the probability density function is of this form, but for reasons of convenience, we're not going to use the letters a, b, and c for these constants. Well, what are we going to use? So we'll write it as f of x is going to be x to the alpha minus 1. So alpha plays the role of a plus 1. E to the minus x over beta. So beta plays the role of 1 over b. We use this in part so that when alpha equals 1, this corresponds to an exponential variable. There, this first term doesn't arise if alpha is equal to 1, and we just are going to have the exponential variable with beta equals 1 over lambda. And then we need some normalization factor. So the normalization, which is in essence just the integral of that term right there, turns out to be 1 over beta to the alpha, the gamma function evaluated at alpha. So this gamma function, this is the gamma function, whereby this random variable gets its name. This is a function which interpolates between the values of the factorial function, among other things. It has lots of interesting, nice properties. But for us, this is just what happens to come up when you solve this integral, when you integrate this factor to get your normalization factor. All right. So, like for example, if we let, as I was saying, if we let alpha equal 1, beta equals lambda inverse, then we get an exponential function. If you let, another nice case is if you let beta equal 2, and if 2 alpha equals nu is some integer, then this thing is what's called the chi-square function, chi-square distribution. with new degrees of freedom. So new should be actually an integer, at least one, a natural number, or whatever you want to call it. All right. So these are the gamma random variables. Gamma random variables are really interesting. They come up all over the place. They're just really useful. And in particular, it's going to be nice to also write down their moment generating function, which is going to help us recognize these random variables when we see them. So the moment generating function of a, so this is for, for your general variable of that sort, is of the form 1 minus beta t to the minus alpha. So it's the very nice little moment generating function for this guy. So what you see, for example, like let's make a nice little observation. Remember that if you have independent random variables and you take their sum, then the moment generating function of their sum is the product of the moment generating functions of the two variables. So for example, if we have, if we're given identical exponential variables x1 through xn, for example, where where they each have the probability density function f of x is lambda e to the minus lambda x. And what happens if we take their sum? So the moment generating function of their sum will be the product of the moment generating functions. Okay, I guess you might be wondering, like, why am I doing this? I mean, that's a natural question. What am I doing? Maybe I didn't make that clear. I know I didn't actually. But what I'm trying to explicate a little bit is that these moment generating functions are very useful because they help us recognize other random variables around. And so, for example, like, what if we have a sum of exponential random variables? What kind of a random variable is that going to be? Is it going to be another exponential random variable? Is it going to be something else? How do we figure out what it's going to be? We can actually figure it out by looking at its moment generating function and just thinking like, have I seen that moment generating function before? So let's do that. Let's grab a sum of n exponential variables, add up their moment generating, add them up. The moment generating function we get is the product of the moment generating functions. We know that the exponential guy has a moment generating function given by this, where alpha is 1 and beta is lambda inverse. And so we get that this is a product of 1 minus beta is lambda inverse. Alpha is equal to 1. You have a product of these where I goes from 1 to n. You multiply those all together, you get 1 minus lambda inverse t to the minus n. And we think, have I seen that before? Have I seen that before? And we're like, oh, actually, yeah, it's like right here. It's another one of these. It's another one of those. What do we get? That tells us that the sum of these xi's, I equals 0 to n, 1 to n, excuse me, is now a gamma variable with alpha being, instead of 1, it's being n, and beta being lambda inverse. And so you can see that these gammas naturally arise when you take sums of exponential variables. Another place that they arise is if you have a standard normal variable. If z is a, oh, I haven't said what a standard normal variable is. That's my next kind of function. Okay, but I guess we're done with the gamma variables, and now we'll take a look at the normal variables. All right, and here we are at the uber important normal random variable. The normal random variable, x, a normal random variable, means that it has a probability density function which is of the form E. Well, let me just like give the very specific formula with the standard letters and all that. E to the minus 1/2 x minus mu over sigma squared. That's basically what it looks like, but then you have to have a normalization factor in front so that the integral is equal to 1. That normalization factor ends up being 1 over sigma square root 2 pi. And this is a very specific, this is a very specific particular random variable. The reason that we write it like this, of course, is because this has variance sigma squared and mean mu. And this is a very important random variable because it comes up like all the time in this in the central limit theorem. So the point being that if you grab any random variable, if you have a bunch of identical random variables which are independent, and you add a bunch of them up, and then you kind of renormalize them so that they, let's say, so that their mean is some fixed thing and their standard deviation is some fixed thing by just rescaling and shifting if needed, then it looks closer and closer to a normal random variable. This is, so we'll remind you of that very soon. But in any case, this normal random variable comes up a lot in terms of repeated measurements of any other random variable that you might think of. Okay, so this is the normal random variable. I'll mention what its moment generating function is. E to the mu t plus 1/2 sigma squared t squared. Okay, so you get this nice moment generating function. And knowing this moment generating function, again, gives us some interesting observations about how to locate normal these normal random variables when they arise, like in nature. So like, for example, like let's suppose x1 is a normal random variable with some particular values, sigma 1 and mu 1, sigma 1 squared and mu 1, we're going to call it, and x2 is a normal random variable with some other variance in mean. Then I might ask, what happens if I consider the random variable x1 plus x2? Let's assume that they're independent. If they're independent, then we know that the moment generating function of the sum is the product of the moment generating functions. So the moment generating function of this is the moment generating function of one times the moment generating function of the other. And well, let's see, what does that give me? That says that this is e to the mu 1 t plus 1/2 sigma 1 squared t squared times e to the mu 2 t plus 1/2 sigma 2 t squared. Okay, and of course we should back up and think, why are we doing this? We're doing this to see if we get lucky and happen to recognize this new moment generating function as one that we've seen before. Of course, we're going to get lucky because, we're going to get lucky. Okay, so we'll just add these or multiply these two things together, add the exponents, and we see that we get mu 1 plus mu 2t plus 1/2 sigma 1 squared plus sigma 2 squared. There was supposed to be a square there, t squared. And so I can write this as e to the mu 1 plus mu 2t plus 1/2. I guess I could just write this as square root of sigma 1 squared plus sigma 2 squared squared t squared. And so what do we find? We find that that our I don't know why I said it like that. I didn't really need to say it like that. That's kind of silly. Let me just get rid of that. Okay, so now I wrote the same thing twice and I feel a little silly, but okay, let me just get rid of it. Okay, excuse me. So what do we see? We see that that this is just another one of these, and we find that that x1 plus x2 is a normal random variable with mean mu1 plus mu2, and variance sigma 1 squared plus sigma 2 squared. And boom, that's kind of cool.